So with matter and energy behind us, now we're going to turn our focus towards measurement. Measurement gives the answer to the questions how large, how small, how big, how little, how fast, how slow, how much. These are questions that need to be answered in the scientific enterprise because some of the data that we acquire needs to be quantified. And as it turns out, numbers play a pretty big role in chemistry. Many of the topics that we cover are going to be quantitative. In other words, they have a numerical value associated with them. Just a few concepts that are going to require numbers. When we're talking about units of measurement, when we're talking about quantities that are measured and calculated. Uncertainty in measurement. You will find soon that every measurement that is made has a certain degree of uncertainty in it. The concept of significant figures, as well as dimensional analysis, in which we use conversion factors in order to solve problems. So, how important are numbers to chemistry, and more specifically to the concept of measurement? Well, a wise man once said, numbers without units are meaningless in measurement. I don't know who that young man is, but by golly, words to live by. If we're talking about measurement, if we're talking about quantifying values, then simply putting a number out there means very little. We need units as well as our numbers. If, for instance, you were lost and you were calling someone and asking them to pick you up, and they said, okay, that's okay, I'll be there in 5. Now, you may assume that they mean 5 minutes, but they could be several hundred miles away and mean well, they'll be there in 5 hours. They could be on another continent and mean I'll be there in 5 days. So to simply say 5 to represent a measurement of time is a little shaky at best. Numbers without units are meaningless in measurement. If you remember nothing about this slide, please remember that quote. The standard system of units that we use in the scientific community is known as the Système International d'Unités, or in English, the International System of Units. Commonly, we simply refer to them as SI units. And for whatever needs to be measured, whatever quantity needs to be measured, there is a different unit associated with it, a different standard unit. Some of those units are listed below. Most importantly, for us moving forward, the standard unit of length in the SI system is the meter. The standard unit of mass is the kilogram, not the gram, but the kilogram. The standard unit of temperature is the Kelvin, one that perhaps we're not familiar with. The standard unit of time is the second. And the standard unit for the amount of substance is a measurement called, or rather a unit known as the mole. And trust me, before all is said and done, we will know a great deal about the mole. Now, these units and the measurements themselves have their roots in the metric system. The metric system was established in the late 1700s in an attempt to establish a standardized system of measurements so that everybody would be making measurements in the same set of units. Everybody needs to be on the same page. If somebody is measuring length in feet and somebody is measuring length in inches and somebody is measuring length in yards, and even more specifically, if somebody's inch is different than another person's inch, then you're going to have problems. So the metric system attempted to remove that problem. And you'll see that some of these standard units in the metric system are the same or carried over to the Système International des Unités, or the SI units, when they were established in 1960. You'll notice that the meter is the standard unit of measurement. The temperature standard is the degrees Celsius or the Kelvin. And notably, we'll see that the unit of volume, the amount of space that something occupies, is a derived unit whose units are the cubic centimeter or sometimes the liter. Now, from time to time, we'll need to take those base units, those standard units, and amplify them. For example, you wouldn't talk about the distance between Dothan, Alabama, and Seattle, Washington in meters. It's a very large measurement. At the same time, you wouldn't talk about the length of a snail in meters. It's a very small measurement. So sometimes prefixes need to be used in order to convert those base units into units that are appropriate for the measurement at hand. And here are an example of some of those prefixes. Here we see the prefix peta, meaning 10 to the 15th power, or 10 times 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 10. So that amplifies a measurement. If we're talking about a watt, a unit of power, a petawatt is a really large measurement. It's not just 1 watt, but it's 1 times 10 to the 15th power watts. If you will look at the third prefix, giga, or as it is more correctly pronounced, giga, it is represented by 10 to the 9th power, or 1 billion, as it were. So 1 gigawatt is 1 times 10 to the 19th watts, or 1 billion watts. If anybody's ever seen Back to the Future, then perhaps you will remember that Doc Brown needed 1.21 gigawatts worth of power in order to activate the flux capacitor. I fear that I'm losing some of you, so I'll move on. We also see prefixes like kilo and deci and centi and milli, which we may be familiar with. King Henry died drinking chocolate milk. Seems to be a mnemonic device that was used for many of us to remember a series of these metric prefixes. And in the world of science, perhaps we need to make really small measurements. So we continue down the spectrum with some really small prefixes, prefixes that are used to minimize the extent of a measurement. So a nanometer is 1 billionth of a meter. A picometer is 1 trillionth of a meter. We talk about nano and pico. Now we're talking about things on the order of the size of atoms and molecules. So there are going to be some basic units that we need to discuss in general. Mass, for example, is one of them. We already know that matter is anything that takes up space and has mass. So what is mass? Well, mass is a measure of the amount of material in a given substance. The SI unit for mass is the kilogram. Length is a measure of distance. The standard unit in the SI system of length is the meter. Now, volume is not a standard unit. It is, however, what we call a derived unit. If we take a cube, and our geometry doesn't fail us, the idea of determining the volume of a cube is that it is the length times the width times the height. So if those 3 measurements are all given in the standard unit of length, the meter, then the volume, the amount of space that the cube takes up, would be in meters times meters times meters, or meters cubed, also known as cubic meters. Now, The cubic meter is a large measurement, relatively speaking. Think about laying a meter stick down, and then think about laying a meter stick down at a 90-degree angle, and then think about standing a meter stick up. Now, if you look at the amount of space that that cube would take up, it may be on the order of a deep freezer, a decently sized deep freezer at that. Well, when we're talking about the volume of liquids, solids that are involved in chemical reactions, perhaps we're not dealing with that big of a volume. So we need to use, once again, different measurements, or use those metric prefixes to modify our measurements. The cubic centimeter is also known as the milliliter. A cubic decimeter is also known as a liter. And most commonly, we find ourselves using the milliliter and the liter in terms of volume. If we were to venture into the lab, then we would see that there are various pieces of glassware that can be used in order to deliver and determine volume. A graduated cylinder, a burette, and a pipette are three that find themselves used commonly in the scientific lab. A volumetric flask is used to hold a certain volume, while the others are used to deliver a certain volume. Temperature is another measurement that is common to chemistry. Temperature is, well, in general, it's considered how hot or how cold a substance is. At the same time, more scientifically speaking, we would say that temperature is a measure of the average kinetic energy of all of the particles that make up a given substance. On the right-hand side of this slide, we see three different temperature scales. We see the Kelvin scale, the Celsius scale, and the Fahrenheit scale. Scientifically speaking, the Celsius and Kelvin scales are most often used. If you'll remember, the metric system has either the Celsius scale or the Kelvin scale as the standard unit. Now, the Celsius scale is based on the properties of water. 0 degrees Celsius represents the freezing point of water, and 100 degrees Celsius represents the boiling point of water. It was developed by Anders Celsius. Well, if the Celsius scale was developed by Anders Celsius, then it shouldn't surprise you that the Kelvin scale was developed by William Thomson, a gentleman whose title was Lord Kelvin. And instead, it's based on the properties of gases. Fundamentally, there has to be a temperature that is the lowest possible temperature. If temperature is a measure of the average kinetic energy, well, what happens if you have less energy and less energy and less energy? Well, then you would have a lower temperature, and a lower temperature still. Well, what happens when you have no energy? Well, that's the bottom of your temperature scale. The Kelvin scale has 0 as the absolute lowest possible temperature. It's called absolute 0. And please note that the unit of Celsius is the degree Celsius. The unit of Kelvin is simply the Kelvin. You do not see a tiny little degree mark beside the letter K. If I hear you say degrees Kelvin, I might get a little angry. Not angry, but just don't say degrees Kelvin, okay? The only way that you can say degrees Kelvin is if you have a friend named Kelvin who just attained his bachelor's and his master's and his PhD. And then you can say, congratulations, did you realize how many degrees Kelvin just received? That's it. That's the only time I want to hear you say degrees Kelvin. Please do not say degrees Kelvin. The unit is simply the Kelvin. And if you have a temperature in degrees Celsius and you want to convert that temperature to Kelvin, you would simply add 273.15. More often, we would simply round that to adding 273. K is equal to C plus 273. It's a nice little sing-song if you need it. Now, the Fahrenheit scale is one that we commonly use in our everyday lives, but it's not one that is oftentimes used in scientific measurements. If I say, oh man, the weather outside, it's 37 degrees outside. Well, if I mean 37 degrees Fahrenheit, then that's a really, 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 really cold day in Alabama. If I say 37 degrees and I mean 37 degrees Celsius, well, that's a really, 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 really warm day in Alabama. So if we're talking about degrees Fahrenheit and degrees Celsius, there's a way that we can convert between the two scales. If you know the temperature in degrees Celsius, simply multiply that by 9/5 or 1.8, and then add the number 32. All right? The order of operations is very important. You do the multiplication first, and then you add 32. If instead you know the temperature in degrees Fahrenheit and you want to know the temperature in degrees Celsius, then you would take the temperature in Fahrenheit, subtract 32 from it, and then multiply by 5/9, which is the same as dividing by 1.8. You'll notice again that the order of operations suggests that this time we deal with the 32 first, since it is in parentheses. And please excuse my dear Aunt Sophia, I don't have an aunt named Sally, would suggest that we do what's in parentheses first. So when converting from Celsius to Fahrenheit, we deal with the 32 last. When converting from Fahrenheit to Celsius, we deal with the 32 first. Briefly, we will speak of the standard units of energy. The standard unit in the SI system is the joule. Since a joule is a relatively small measurement, then the kilojoule or the kilojoule is oftentimes used. Now, in years past, the calorie was a standard unit of energy. So just when you thought that a calorie was something that a substance possessed, that slice of vanilla bean cheesecake from TGI Fridays, you know the one I'm talking about, the one with the little white chocolate sprinkles on top. Well, when we say that that slice of cheesecake has a certain number of calories, what we're actually saying is that that caloric value is the amount of energy that you need to put out in order to burn it off or in order to metabolize that slice of cheesecake. So a calorie is a relatively small unit of measurement, but we shouldn't confuse a calorie with a calorie. I don't know if you're just listening, that doesn't make a whole lot of sense. We shouldn't confuse a little c calorie with the nutritional calorie, the big C. The big C calorie, the calorie that you read on the back of a bottle of cherry vanilla Coke. Well, that is a big C calorie. That is a kilocalorie. That is 1,000 little c calories. Why would they do that? Why would they add that confusion? Well, it's off by a factor of 1,000. So which of these sounds better? Hey, would you like a bottle of cherry vanilla Coke? It's got 200 calories. Or, hey, would you like a bottle of cherry vanilla Coke? It's got 200,000 calories, but they're little c calories. No, that sounds, no, just no, all right. Another derived unit is density. Density is a physical property of a substance in which we refer to the amount of space that it takes up as well as how much substance there is. Mathematically, Density is the ratio of an object's mass to its volume. How massive something is for the amount of space that it takes up. Imagine a golf ball, imagine a ping pong ball. Both of them take up about the same amount of space, and otherwise they have about the same volume. But since the golf ball has more mass, we would say that it is more dense. Again, let's take a look at a basketball and a bowling ball. A basketball and a bowling ball take up about the same amount of space, but since the bowling ball is typically heavier, typically more massive, we would say that there is more mass per unit volume. The bowling ball is denser. And on the right-hand side, we see a table of densities for various substances at 25 degrees Celsius. Now, there are two types of numbers that we're going to encounter in science. There are exact numbers and inexact numbers. Exact numbers are counts. For example, if I asked how many people there are on my roster, then I would count 1 person, 2 person, 3 person, 4 person. That is an exact value. An inexact value is derived from a measurement. If I ask how far away I am from Troy University's campus in Montgomery, then that is a measurement. The number that is associated with that distance is going to be an inexact number, because all measurements are inherently uncertain to a degree. If I were to step on a scale, okay, wait a minute, let me back that up. If a random person were to step on a scale, and that scale were to read 225 pounds, if that scale is presented in whole numbers, we cannot assume that that person weighs exactly 225 pounds. That person may weigh 224.8 pounds. That person may weigh 225.2 pounds. But within the realm of certainty, we can say that that person weighs 225 pounds. But there is a level of uncertainty in the measurement. We don't know exactly. So the last measured digit is generally considered to be reliable, but not exact. True or false? When we make measurements, we want to make measurements that are precise. Here's another one. True or false? When we make measurements, we would like to make measurements that are accurate. Well, we could say true to both of those statements, because accuracy and precision both indicate a level of agreement, a level of goodness. The terms are very different in what their agreement is. Accuracy is the agreement of a measurement with the actual or known value, with the correct or the true value. Precision is how closely an individual measurement agrees within a given set of measurements. So, for example, let's take that person who stood on the scale. If that person knows that they weigh 225 pounds, and they stand on the scale and it reads 225 pounds, then guess what? That measurement was accurate. It shows that that scale can accurately determine the measurement of that person's weight. Now, if that person steps on the scale and it reads 214 pounds, then that scale is not accurate. If that person steps on the scale and it says 292 pounds, then that scale is not accurate. It doesn't agree with the actual known value. Precision deals with the repeatability of a measurement. You can't make a single measurement and have it considered to be precise. You have to make a measurement over and over and over again and get the same or a similar result. Let's take our person standing on the scale. If the person who weighs 225 pounds stands on the scale and they appear to weigh 214 pounds, if they step off the scale and then 6 minutes later they jump back on and it says 214 pounds, and they jump off the scale and then they jump back on the scale and it continues to read 214 pounds, then those measurements are precise because you're taking the same measurement, you're making the same measurement over and over again and getting the same or a similar result. It doesn't matter that it's not the correct value, but if it's the same value, then it is considered to be precise. It would not be considered to be accurate if the person in fact weighed 225 pounds. Any science teacher worth his or her salt, when talking about the difference between accuracy and precision, is going to present you with one of two examples. Either the game of horseshoes or a dartboard. If you look at the three dartboards on the right, you will see that at the bottom we see 3 dart throws, none of which have achieved the target value of the center bullseye, none of which are near one another. So what we have here is a case of poor accuracy because they're not near the target, and poor precision because they're not near each other. In the second image, we see poor accuracy because the 3 throws are nowhere near the center, but they are near each other, right? Some of you may refer to that as a tight grouping in military terms. The top image, oh, that's the one that we're shooting for. We see good accuracy and good precision. We get the right result, and when we do it over and over and over again, we continue to get the right result. Since all measurements have some degree of uncertainty or error associated with them, then it's useful to indicate the exactness of the measurement. This exactness is reflected in the number of significant figures. Now, it's important when using calculated values, those inexact numbers, that we pay attention to the number of significant figures. Otherwise, we might end up overestimating how good or how accurate our measurement actually is. If I take a meter stick and I measure the height of a stool, and it goes about halfway up the meter stick, then I could quickly say that that stool is about half a meter tall. I could say that it is 0.5 meters tall. Without going into great detail, without using much more well-defined measuring tools, I can't say that it is 0.4895782333391 meters. That is way too exact, and I'm not sure to that level of certainty at all. I only know that it's about a half a meter tall. So it's important, very important, that we pay attention to significant figures as they reflect the certainty of a measurement. Now, in a reported measurement, there are certain numbers that are considered to be significant and some that are considered to be insignificant or not significant. Well, here are the guidelines for significant figures. Number 1, all non-zero digits are significant. So if I report a value as being 533 meters, then all 3 of those digits would be considered to be significant. The only time when we have concerns with significant figures is when zeros are involved. Sometimes zeros mean something, and sometimes zeros are just placeholders. Sometimes they are insignificant. Well, rule number 2 suggests that zeros in between non-zero digits are significant. Rule number 3, zeros at the beginning of a number are never significant. So if I were to say 0.0000007 miles, all of those zeros are at the beginning of a number. It's before you hit the first non-zero digit. All of those zeros would not be significant. None of those zeros would be significant. The fourth rule, zeros at the end of a number are significant if it contains a decimal point. 500.0. That last zero is significant. 592.580. That last zero is significant. 382,933.00000. That last zero would be significant. And since those other zeros fall in between significant figures, then they would be considered significant as well. The problem lies when we have whole numbers that end in 0. 300. How many of those values are significant? 290. How many of those are significant? 500,000. How many of those digits are significant? Well, the general rule of thumb is if we don't have a bar atop one of those zeros, then all of those zeros would be considered insignificant. I will send you a handout in more detail with regards to significant figures. Now, when dealing with calculations, the least certain measurement is the one that's going to limit the number of significant figures in your final answer. And that's going to differ depending on whether you're doing addition and subtraction or whether you're doing multiplication and division. When adding or subtracting numbers in significant figures, and that means measurements, the answers are rounded to the least significant decimal place. When multiplying or dividing, your answer will be rounded to the same number of digits as the measurement that has the fewest number of significant figures. And once again, I will be supplying you a handout that speaks to this in more detail. Finally, the concept of dimensional analysis. Dimensional analysis is a technique that we use in order to change units for a particular measurement. Perhaps I wanted to know how long a marathon is in meters. I know that a marathon is 26.2 miles, but I want to know what that measurement is in meters. So in order to do that, I would use a conversion factor. A conversion factor is the ratio of two equal measurements that are used to convert from one set of units to another. If you look on the screen, you will see the ratio of 1 inch to 2.54 centimeters. 1 inch is the same as 2.54 centimeters. So if you have something divided by something that is equal to it, then that value is going to be 1. 1 inch divided by 1 inch is equal to 1. 2.54 centimeters divided by 2.54 centimeters is equal to 1. Anything divided by itself, is equal to 1. So since we have a ratio that is equal to 1, we can multiply a measurement by that ratio in order to get rid of the units that we don't want and keep the units that we do want. Sometimes we may need to use multiple conversions. If we do so, then we would need to know the equalities, the ratios for the various measurements. Well, that pretty much sums up our portion of Chapter 1 on measurement. I will be presenting more information on dimensional analysis and conversion factors in a subsequent lecture. Thank you very much, and again, have a great day. Stay safe.